Hello friends, welcome to my channel. So this video is the continuation of my last video. In the last video I discussed about the Maxwell's equation and I also derived the Maxwell's first equation. So in this video I am going to derive the Maxwell fourth equation. So please stay with us, like and subscribe my channel to get the more updates. So these are the four Maxwell's equation that I already discussed in my last video. So these are the integral form of the Maxwell's equation. And these are the differential form of the Maxwell's equation. So in this video our aim is to derive that equation del cross B equal to J plus del D by delta T. It means from the integral form to the differential form. Okay. So first we have to discuss what is equation of continuity, because that equation of continuity we are going to use in to derive the Maxwell's equation. So the formula is that divergence J equal to minus del rho by del T. So what is the physical meaning of this thing? Okay. So already we discussed in my divergence chapter that there is three type of divergence. One is positive, one is negative, and another is zero. So positive means if the flux is in the outwards direction. Okay. So if it is in outwards direction, it means the volume is increases. Understood now? Because the direction is like this. So it means if the divergence is positive, then the direction is in outwards. So outwards means its volume increases. So when the volume increases, then what happens? The density decreases. So for positive divergence, my density getting decreased. So density rho is negative. Now the next case is the negative divergence. Negative divergence means the flux are in inward direction. It is in this direction. So when the flux are in inwards direction, it means the flux is coming in that direction. So it means my density increases. Understood? So when my density increases, it means this is the negative divergence. So in case of negative divergence, we get the density is zero. Oh, sorry, positive. Understood? So this is the most important thing. For the positive divergence means the flux are in outwards direction. So if the outwards direction means my area is increases, so my area is increases means my density decreases. The negative divergence means the flux are in inwards direction. So if it is inwards direction means my density is increases. So if the density is increases, then we can say this is the negative divergence. And the zero divergence means if the my incoming and outgoing are same, then we can say this is the zero divergence. So now the correlation between this divergence and the equation of continuity is that you see this is the divergence J. It means this is a positive divergence. Okay. So if the divergence is positive, it means my flux are in outwards direction. It is outwards direction. So it means the flux of this area is increases. It means that volume is increases. So this is the positive divergence. So volume increases. It means the density is negative. That's why you can write divergence J equal to minus del rho by del T. So this is the positive divergences. When anything in the positive divergence, in that case we can say the density is getting reduced. Okay, so I think you understand what is the physical meaning of the equation of continuity. Okay. So now in the next we can. So now to derive the Maxwell's fourth equation, we are going to use some formulas, and the formulas are, the first formula is J equal to I by A. So A is the area, so I can write it as I equal to in the integral from J dot ds. So this is the current density formula. And one more formula is the Stokes theorem. So you can see the formula is A dot dl equal to del cross A ds. So if I convert my line integral to the surface integral, then I use the Stokes theorem. So using the Stokes theorem, I can convert line integral to surface integral. So now we can see according to the Ampere circuit law. So this is the Ampere, the first Ampere circuit law is that B dot dl equal to mu naught I. So this line is same, just I write the B dot dl and I can replace I as a J dot ds. So I can just write mu naught integration J dot ds. So you see this part is surface integral ds and this part is line integral. So I have to convert that part into the surface integral. So how I can convert? Using the Stokes theorem. So I just convert V dot dl as a surface integral and I am writing it here del cross B ds. I just convert that v dot dl to del cross b ds using Stokes theorem, and my remaining part is same. So you see now my this part and right hand side and left hand side are in the surface integral. So just I can simplify that value. So I can write it like this: del cross b equal to mu dot j, mu not j, because you see these are the same surface integral. So I can write it like this: del cross b equal to mu dot j. Then I also write it like this: del cross h equal to j. So we know that our b by epsilon naught mu naught equal to h. So b is the magnetic field and h is the strength of that magnetic field. So this is my del cross h equal to j, and this is in case of steady case. It means according to the Ampere circuit law, we can write this as a del cross h equal to j. Okay. So now in the next, so in the last slide, I found that according to the Ampere circuit law, that del cross h equal to j. So this is for the steady case. But when Maxwell performed experiment, we know that one more extra term is there, and that term is the displacement current. So it means for the changing electric current density, okay, we get one extra term according to the Ampere Maxwell's law, and that term is a Z-dash. Till now we don't know what is the value of the Z-dash, just I read as a Z-dash, okay, and that term is a displacement current part. I already discussed the displacement current in my videos, okay. So this is my modified version of Ampere circuital law, or we can say Ampere Maxwell law. The modified version is del cross h equal to j plus z dash. This is up to j is my Ampere circuital law, and j plus z is the modified Ampere circuital law. So now I'm taking the divergence of this equation A. So what is the divergence? Del cross h equal to del dot j plus z dash. This term is 0 because we know that the dot product of any curl is a 0, and I think you can find it from your mathematical physics chapter. So this is 0, so I can write this part as a 0, and this is same. It means del j plus del j dash. So this part is 0, and we can write del j. So from the equation of continuity, what we get? Equation of continuity, we get the divergence j equal to minus del rho by del t. That part I already discussed. Okay, so I just put that del dot j value is there minus del rho by del t equal to del j dash. So just I side change this value. So what I get that del j dash equal to del rho by del t. Okay, so I think you understand how we get the del j dash equal to del rho by del t. So now we know that del z dash equal to del rho by del t. So from that Maxwell's first equation, we know that del dot d equal to rho. So I just put the value of rho. It means I just replace that value here. So what I get that our del z dash equal to d by dt, and I just replace this rho as a del dot d. So after simplification, I get del z dash equal to del d by dt d, and it means this is our z dash equal to del by del t d. So what is my value of z dash? So we know that z dash is d by dt into d. It means d dt by dt. So we know that from our equation A. So what is the equation? Equation A says that del cross h equal to j plus z dash. Okay. So this equation is the modified Ampere circuital law. So I now put that z dash value in my this equation. So what in my equation A. So this is the equation A. Okay. So what I get if I put the z dash value? So del cross h is same, j is same, and what is the value of z dash? Z dash is the del d by del t. So this is the differential form of the Maxwell's fourth equation. Okay, and this j, if I write del cross h equal to j, it means it is a Ampere circuital law, and if I write del cross h equal to j plus del d by del t, so this is the modified version of Ampere circuital law, or also we can say that this is the Ampere Maxwell's law, and this is the differential form of the Ampere Maxwell's law. Okay. So thanks for watching my video. Please like and subscribe my channel to get the more updates. Thanks.